All right, I'll do another one now. It's a little wonkier. Well, actually, this one's not that wonky. This one's pretty straightforward, but it's a good way to think about this. Let's say I have a ring. It's like a little ring rotating of mass m and radius r. What's the moment of inertia of that thing around an axis through its center? Now, it's not a disk, it's just a ring. So all this is empty space, and it has a radius of r. Okay, well, let's think about how I would go about doing this. I want to take a little mass dm. I'm going to write it as having some kind of thickness, even though it really doesn't, just for the sake of it. Let's say I'm over here and I have a little bit of mass dm, just like I did on the rod, a distance r away. This is my dm. Okay, well, I have that little dm, and I want to do my r squared dm integral over all the dm's, right? And this one actually is pretty cool because there's a symmetry here that prevents you from having to do anything fancy. So let's just start out by writing the integral. I equals integral of r squared dm over all the little dm's. We're going to do it for every little dm and add it up. The first thing you might notice, different than with the rod, when we did the rod, remember, when we did the rod, every dm had a different x value. So we really needed to do that integral because we were integrating over the dx, and the x was, the dm kind of went along the dx, and the x values changed for every dm. Here, that's not really the case, right? If I look at my dm, my distance from the rotation axis is the same because I'm on the ring of a circle. So the r is not a function of where that mass is going to be. That's really cool. I can just, because of that, I can do this. I can pull that out as just the r is just the radius of the ring squared. And then it just becomes the integral of dm. Well, the integral of dm is just the mass of the ring. And so the moment of inertia of a ring rotating about its center of mass is just mr squared. Super simple. Same as it, and this makes sense for a lot of reasons, right? Because it's all that mass. We don't remember when we went back to our kinetic energy thing. I wish I don't know where I put that little kinetic energy derivation that I did with all the dots. But yet, when you have just one mass, it has a velocity, and the kinetic energy is 1/2 mv squared. Well, all the mass is at the same distance. So even though it's rotating with an angular velocity omega, every bit of mass on that ring is moving at the same velocity. So I could just do 1/2 mv squared for the kinetic energy. In other words, this acts just like, kind of like a big smeared out bunch of mass at the same distance. So that's kind of cool. Okay. If you want to now use the parallel axis theorem, you could shift that rotation axis over here, for example, and like spin the ring like around, you know, it would like roll around on that rod. That's where you would add another mr squared to that. So the I around point O would be the I around the center of mass, which is mr squared, plus how much you've shifted it over, which is another mr squared. So it would be 2mr squared. That's cool. All right, next video, we're going to keep going because this is actually kind of fun. Bye.